Somewhere under 15 miles of ice, in an ocean no light has ever touched, carbon is moving. Not delivered by a comet, not painted on by radiation, rising. Webb turned its mirror toward a frozen moon and read a chemical signature that should not exist on a world we long called dead. Carbon dioxide, gathered in the scarred terrain where the ice cracked and healed, carrying the fingerprint of the sea beneath. Tonight, we follow that carbon down into the dark water nobody has ever seen. If a calm voice unraveling the universe helps you drift, subscribe so you never miss the next descent. And tell me where you are listening from and what time glows on your clock. There is a story we tell ourselves about life in the universe, and it goes something like this. Life is rare, life is precious. Life is a thin green film that managed to form on one warm, wet planet, ours. And if we ever want to find it anywhere else, we will have to look across distances so vast they break the imagination. We point our telescopes at other stars. We talk about exoplanets, faraway worlds orbiting suns that are not our sun, and we wonder which of them might be a second Earth. The whole search feels like a search outward, away from home, into the deep night between the stars. That is the comfortable picture. That is the belief most of us carry without ever quite examining it. And tonight, gently, I want to take that belief apart, because the most promising place to look for life beyond Earth may not be a distant planet at all. It may not require a faster rocket or a longer journey or 1,000-year wait. It may be sitting in our own solar system, close enough that we have already launched a spacecraft toward it, close enough that a telescope built to study the dawn of the universe could turn around, look inward, and read its chemistry. It is a small moon. It is wrapped in ice, and for a very long time we looked right past it. Let me bring the camera home. Forget the distant stars for a moment. Travel only as far as Jupiter, the giant of our solar system, a planet so large that more than 1,000 Earths could fit inside it. Jupiter is a world of storms, a banded sphere of swirling gas with a red spot wider than our entire planet, and around it circles a small crowd of moons, dozens of them. Most are little more than captured rocks, dark and cratered and unremarkable. But 4 of them are different. 4 of them are worlds in their own right, large and round and ancient. And they were the first moons anyone ever saw orbiting another planet. Galileo found them in the year 1610 with a crude telescope and a stubborn mind. And in doing so, he quietly shattered the old idea that everything in the heavens revolved around the earth. Among those 4, one shines with a particular pale brightness. Its name is Europa. Europa is not large. It is slightly smaller than our own moon, a modest sphere you could drive across in a few days if there were any roads, which of course there are not. From a distance, it looks almost gentle. It is one of the smoothest objects in the entire solar system, a polished marble of ice reflecting sunlight so brightly that it glows. Run your eye across its surface, and you find a strange and beautiful thing. There are very few craters, almost none, and that absence, that quiet emptiness where there should be scars, is the first thread that, once you pull it, begins to unravel everything. Think about what a crater means. Every airless world in our solar system has been bombarded for billions of years by asteroids and comets and stray debris. Our own moon is a graveyard of impacts, pockmarked from pole to pole, its face a record of every blow it has ever taken. The same is true of Mercury, of Mars, of nearly every solid surface we have ever photographed. Craters are the default. Craters are what happens when a surface is old and unchanging, sitting still long enough to collect the bruises of deep time. So, when you find a world with almost no craters, the conclusion is unavoidable and a little unsettling. The surface must be young. Something must be erasing the scars. Something must be resurfacing this moon, smoothing it over, wiping the record clean again and again across geological time. But for decades, nobody knew that. For most of human history, Europa was nothing more than a point of light, a faint companion to Jupiter visible only as a moving star. Even through the great telescopes of the 19th and early 20th centuries, it remained a blur, a tiny bright disk with no features anyone could resolve. Astronomers knew it was there. They knew roughly how big it was and how fast it moved. But what it actually looked like, what it was made of, what hid beneath its glow, all of that was guesswork, and the guesses were modest. A ball of ice and rock. A frozen, dead, uninteresting little world. There were larger mysteries to chase. Europa waited in the cold, ignored. There is a lesson in that long neglect, and it is a lesson worth carrying with you. The reason Europa was ignored for so long was not that the evidence was hidden. The evidence was there in plain sight. A bright moon visible to anyone with a small telescope, a point of light Galileo himself had watched 4 centuries ago. The reason it was ignored was that we did not expect to find anything, and what we do not expect, we tend not to look for. The assumption of a dead, frozen solar system acted like a kind of blindness. It told us in advance that the outer moons were uninteresting, and so we did not bother to study them closely. And so we found nothing, which confirmed the assumption, which deepened the neglect. This is one of the quiet traps of the human mind. We see what we expect to see, and the most extraordinary things can sit in front of us for generations, unremarked, simply because we have decided in advance that they cannot be there. It took spacecraft, hard data, undeniable images to break the spell. And once the spell was broken, Europa transformed before our eyes from the least interesting kind of world into one of the most interesting places in the entire solar system, without itself having changed at all. Only our attention had changed. Only our willingness to look. The first real change came in the 1970s, when humanity did something extraordinary. We built 2 spacecraft, named them Voyager, and flung them out past the orbit of Mars toward the outer planets. These were not telescopes peering from afar. These were travelers, machines carrying cameras across hundreds of millions of miles to fly directly past the giant worlds and send home the first close portraits anyone had ever seen. When Voyager swept through the Jupiter system in 1979, it turned its cameras on the 4 Galilean moons, and one by one they resolved from points of light into places. Real places with real surfaces, each one stranger than the last. And Europa, when it finally came into focus, stopped people cold. Here was that smooth, bright ball, yes, but it was not blank. Across its pale face ran a vast network of lines. Long reddish-brown streaks, crossing and recrossing, stretching for thousands of miles, branching and tangling like the cracks in a shattered eggshell that had somehow been glued back together. Nothing else in the solar system looked quite like it. There were no tall mountains. There were no deep canyons. There was hardly any vertical relief at all, almost no up and down, just this flat, bright expanse scored with countless dark fractures. It looked, more than anything, like a frozen sea, like the surface of an ice-covered ocean on Earth, the kind that forms over the polar regions, cracking and shifting and refreezing through the long winter. That resemblance was not lost on the scientists who studied the images. The mind reaches for the familiar, and the most familiar thing those patterns resembled was sea ice. But resemblance is not proof, and the Voyager flybys were brief, just a fast pass and a handful of pictures before the spacecraft hurtled onward towards Saturn. The images raised the question without answering it. Why was this moon so smooth? Why were there so few craters? What were those endless cracks? And what, if anything, lay beneath them? Voyager could not stay long enough to find out. It gave us a glimpse and a mystery, and then it was gone, carrying the question outward into the dark. It is worth lingering on how radical the change in perspective really was, because the human mind does not surrender its assumptions easily. For generations, the default picture of the outer solar system was a picture of death. Beyond Mars, the thinking went, you entered a realm of frozen wastelands, of airless rocks and lifeless ice, a place where the sun was a distant spark and nothing interesting could ever happen. The giant planets were spectacular, yes, but their moons were assumed to be inert, cratered, geologically finished. Worlds where the last interesting thing had occurred billions of years ago, and where nothing had stirred since. That assumption was not foolish. It fit almost everything we had ever seen. Our own moon is exactly such a place, a beautiful dead museum of ancient impacts. So when Voyager began returning its portraits of the Jovian moons, the expectation was simply more of the same, more cratered ice, more frozen stillness, more museums of the long-dead past. But the Jovian moons refused to cooperate with that expectation, and Europa refused most stubbornly of all. Consider how it looked beside its siblings. There was Io, the innermost of the four, a moon caught in even fiercer tidal flexing than Europa, and Voyager, caught it in the act of erupting, volcanoes throwing plumes of sulfur hundreds of miles into space, a world turned inside out by heat. There was Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, with its own tangled history written across an ancient grooved surface. There was Callisto, dark and heavily cratered, closer to the dead museum the scientists had expected. And there, between fiery Io and giant Ganymede, was Europa, smooth and bright and almost untouched, a moon that looked less like a frozen relic and more like something freshly made. In the company of its siblings, Europa stood out, not for being the most violent or the largest, but for being the most suspiciously, impossibly young. That youth was the thing that would not let the scientists rest. A surface this smooth, this nearly free of craters, simply could not be old. Across the age of the solar system, Europa must have been struck countless times, just as every other world was struck. The craters should be there, and yet they were not, or there were only a precious few. Something had been erasing them, smoothing the surface, renewing the moon's face across geological time. On Earth we know what keeps a surface young. Geology, moving water, shifting crust, the restless churn of a living planet that buries its scars and lays down fresh terrain. For a moon to keep its face young, something inside it had to be active, had to be moving, had to be reworking the surface from below. And the most natural thing that could do that, the most natural agent of renewal on a world made largely of ice, was water. Liquid water, welling up, freezing over, smoothing the moon again and again like a sea that resurfaces its own ice each winter. For a while the idea simmered. A few researchers began to suggest something almost heretical. What if Europa was not frozen solid all the way through? What if, beneath that bright shell of surface ice, there was liquid water, not a puddle, not a damp layer, an ocean, a genuine, global, planet-wrapping ocean of liquid water, hidden under a roof of ice, kept warm by some source of heat we did not yet understand. It was a bold thought, and at first it sat at the edge of respectability, the kind of idea you mentioned carefully, with caveats, because the obvious objection was overwhelming. Europa is far from the sun. Out at Jupiter, sunlight is dim, only a small fraction of what bathes the Earth. The surface of Europa is brutally cold, hundreds of degrees below freezing. How could liquid water possibly survive in a place like that? Everything we knew said it should be ice all the way down, a solid frozen ball, dead and still. And yet the surface kept whispering otherwise. The smoothness, the missing craters, the cracks that looked so much like floating ice. These were not the features of a world frozen solid and left untouched for billions of years. They were the features of a world that was alive in a geological sense, a world that was moving, renewing itself, hiding something restless beneath its skin. The evidence on the surface pointed, again and again, downward, toward something we could not see. This is the strange position we found ourselves in. We had a moon we had written off as a frozen billiard ball, a smooth, dead marble of no great interest, and the closer we looked, the less dead it seemed. Every new detail deepened the puzzle instead of solving it. The surface was too young, the cracks were too suggestive. The whole face of the moon seemed to be telling us that the story we had assumed, the story of a simple frozen world, was wrong. And the only explanation that fit the clues was an explanation almost too wonderful to take seriously. That beneath the ice, in the cold and the dark, far from the warmth of any sun, there was water, liquid water, the one substance, more than any other, that we associate with the possibility of life. But suggestion is not the same as knowing. A surface that looks like floating sea ice is not the same as an ocean confirmed. To go from a hunch to a hidden sea, science would need more than pretty pictures from a passing spacecraft. It would need a mechanism, a source of heat to keep the water liquid in a place that should be frozen through. It would need direct evidence, some signal from beneath the ice that could not be explained any other way. It would need patience and instruments, and the willingness to take seriously an idea that sounded, on its face, almost impossible. A warm ocean on a frozen moon, 3/4 billion miles from the sun. So here we stand, at the edge of the question that will carry us through everything that follows. We have a small, bright moon that we ignored for centuries, and then, slowly, learned to see. We have a surface that refuses to behave like the surface of a dead world, a face so young and so restless that it can only be hiding something. And we have a possibility that, if it is true, Changes the way we think about life in the universe and about our own loneliness within it. The possibility that the nearest ocean beyond our own planet is not on some distant Earth around a faraway star, but right here in our own solar system, sealed beneath miles of ice on a moon we very nearly never bothered to look at. Notice, too, how completely this reframes the search for life itself. For most of the modern era, when we imagined finding life elsewhere, we imagined a planet, a warm world with a sky and a sea and a sun overhead, a second Earth bathed in starlight, green and blue and breathing. That is the image science fiction gave us. And it is the image that quietly shapes how most of us think about the question. But a moon like Europa proposes something entirely different. It proposes that the place to look might have no sky at all, no sunlight, no open ocean reflecting a star, just darkness and ice and water hidden beneath. If that is where the conditions for life can gather, then we have been searching with the wrong picture in our heads. We have been scanning the distant stars for warm-lit worlds when the more promising cradle may be a cold, dark sea sealed inside a frozen moon, the kind of place we would never have thought to look, the kind of place that might be far more common in the universe than Earth's. And this is why Europa matters so much more than its modest size would suggest. It is not just one curious moon. It is a test of an idea, the idea that life does not require a world like ours, that the recipe can be assembled in the dark, beneath the ice, far from any sun. If that idea is right, the universe becomes a far more crowded and hopeful place, because dark, icy oceans may outnumber sunlit seas 1,000 to 1. Europa is the nearest place to test it. The nearest hidden ocean. The nearest chance to learn whether the conditions for life are rare and precious or quietly common, scattered through the cold like seeds we never noticed. What is under the ice? That is the question. And to answer it, we have to go down, layer by layer, into the cold and the dark, and assemble the case piece by piece, the way the scientists did, until the hidden ocean stops being a dream and becomes something we can almost touch. Notice already how the feeling has shifted. We began with a tidy, comfortable belief that life is rare and distant, and the search must be a search across the stars. And in only a little while that belief has begun to crack, the way the ice of Europa cracks, revealing something restless and unexpected underneath. The dead moon is not dead, the frozen ball is not simply frozen, and the nearest sea beyond our own may be hiding in our own neighborhood. Beneath the skin of ice we can see with a small telescope from a back garden on a clear night. Hold on to that feeling of a settled assumption coming loose, because it is the feeling this whole journey is made of. Stay with me and breathe slowly, because the descent begins now. So let us build the case slowly, the way a careful mind builds it, one beam at a time, until the structure stands on its own and the impossible ocean becomes the only thing that makes sense. We left off with a puzzle, a surface that looks like floating ice, a world too smooth and too young to be frozen solid and forgotten, and a single stubborn objection that seemed to sink the whole idea. Europa is too cold, it is too far from the sun. Liquid water out there should be a fantasy. To save the ocean, we need to find heat. We need to find a furnace burning in a place where there is almost no sunlight at all. And here is where the universe reveals one of its quieter tricks. The sun is not the only way to warm a world. There is another source of heat, ancient and patient and utterly indifferent to distance, and it comes not from light but from gravity. It comes from being squeezed. Picture Europa in its orbit. It circles Jupiter once every 3.5 days, swinging around that enormous planet at tremendous speed. Now, Jupiter is not just large, it is monstrously massive, and its gravity does not pull on Europa evenly. The side of the moon facing Jupiter feels a stronger tug than the side facing away. This difference in pull stretches the moon ever so slightly into a faintly egg-like shape, with the long axis pointing toward the planet. If Europa orbited in a perfect circle, that stretch would simply hold steady, a fixed deformation, and nothing much would happen. But Europa does not orbit in a perfect circle. Its path is gently lopsided, an ellipse, and that small detail changes everything. Because the orbit is not a perfect circle, Europa moves closer to Jupiter and then farther away across each loop. When it swings closer, the gravitational stretch grows stronger and the moon is pulled into a more pronounced shape. When it swings farther, the stretch eases and the moon relaxes a little toward round. Closer, farther, closer, farther, every 3.5 days, forever, the moon is being flexed. It is being kneaded, like a ball of dough worked endlessly between two hands, squeezed and released and squeezed again, billions of times across billions of years. And what happens when you flex a solid thing over and over? It warms. Bend a paperclip back and forth and feel the metal grow hot at the joint. Knead anything stiff enough, fast enough, long enough, and the energy of that constant working turns into heat from the inside. Europa is doing exactly this on a planetary scale. The relentless tidal kneading from Jupiter generates warmth deep within the moon, in its rocky interior, and along the boundary where rock meets ice. This is tidal heating, and it asks nothing of the distant sun. It is heat born purely of motion and gravity and time. It burns in the dark. What keeps Europa's orbit slightly lopsided, you might wonder, instead of settling into a tidy circle? The answer is its neighbors. Europa is caught in a gravitational conversation with two of the other large moons, Io closer in and Ganymede farther out. Their orbits are locked together in a steady mathematical rhythm, each one tugging on the others at regular intervals, and this gentle ongoing tug-of-war keeps all of their orbits from relaxing into perfect circles. The lopsidedness is maintained. The flexing never stops. The furnace stays lit. It is a beautiful and almost musical arrangement. 3 moons keeping each other warm through the simple geometry of how they move. There is a detail here worth dwelling on, because it reveals how subtle and how patient this heating really is. The amount of warmth produced by any single flex of the moon is tiny. If you could stand on Europa and feel one stretch and one relaxation, you would notice nothing at all. No tremor, no warmth, no sign that anything had happened. The deformation is gentle, and the heat from any one cycle is almost nothing. But now multiply that almost nothing by the relentlessness of time. The flexing happens every 3.5 days, without pause, without rest, and it has been happening for billions of years. The solar system is more than 4.5 billion years old, and across that immensity the tiny warmth of each cycle has been deposited again and again and again, an unbroken drumbeat of heat with nowhere to escape quickly through the insulating ice. Small things, repeated without end across deep time, become enormous. A drop of water cannot move a stone, but a drop falling on the same spot for 1,000,000 years will bore straight through it. The tidal heating of Europa is the drop, and the moon's interior is the stone, and the result, summed across the ages, is enough warmth to keep a vast ocean liquid in a place where the sun is only a bright, distant star. So we have found our heat. The objection that seemed fatal, that Europa is too cold and too far from the sun, dissolves once you understand that the sun was never the point. The warmth comes from within, from the endless tidal working of Jupiter's gravity. Now the idea of liquid water beneath the ice is no longer a fantasy. It has a power source. And once you accept that there could be enough warmth to melt ice into water deep inside the moon, the surface clues begin to line up like witnesses telling the same story. Return to that scarred and beautiful face. Look closely at certain regions and you find something remarkable, terrain that geologists came to call chaos terrain, and the name is well earned. In these places, the smooth ice is broken into a jumble of blocks, slabs, and plates of crust that have been shifted, tilted, rotated, and refrozen into a frozen mosaic. Some of these blocks look as though they were rafts, chunks of the surface that broke free, drifted a short distance, and then locked back into place when the surrounding slush froze around them. On Earth, we know exactly what produces patterns like this. Floating ice does. When a frozen sheet sits atop liquid water and the water moves or the ice cracks, slabs break off and raft about and refreeze, leaving precisely this kind of disrupted jigsaw appearance. The chaos terrain on Europa looks like the signature of ice, floating on something liquid underneath. Then there are the great cracks themselves, the long reddish lines that first stunned the Voyager scientists. Study how they behave over time and across the moon, and you find that some of them seem to open and close, to shift position in ways that suggest the crust is not rigidly fixed to the interior, but is instead riding on top of a layer that can move. Picture the ice shell as a loose skin floating over a deep liquid sea, slowly sliding, cracking under stress, healing, cracking again. The pattern of the fractures, the way they curve and branch, and sometimes cut across one another at telling angles, fits a crust that is being pushed and pulled by tides and by the slow churning of an ocean beneath. Every feature points the same direction, down, but surfaces can fool us. A landscape can resemble floating ice without actually floating on anything, and good science does not rest on resemblance alone. To truly confirm a hidden ocean, we needed a probe that could in some sense reach beneath the ice and feel for the water directly. And in the 1990s, we sent one. Its name was Galileo, and unlike the Voyagers, which only flew past, Galileo arrived to stay. It slipped into orbit around Jupiter and spent years circling the giant planet, swinging again and again past the great moons, studying them with patience no flyby could match. And it carried an instrument that would change everything, a magnetometer, a device for measuring magnetic fields. With it, Galileo found a clue hidden not on the surface, but in the invisible space around Europa, a clue that no amount of clever geology could have provided. To understand what Galileo found, you have to know one strange and useful fact about Jupiter. The giant planet is wrapped in an immense magnetic field, vastly stronger than Earth's, and as Jupiter spins, that field sweeps around with it and washes over its moons. Europa sits bathed in Jupiter's magnetism. Now here is the key. When a magnetic field passes through a material that can conduct electricity, it stirs up electric currents inside that material, and those currents in turn create a second magnetic field of their own, a kind of magnetic echo. The technical name is an induced field, but the plain idea is simple. If something inside Europa was conducting electricity, Jupiter's shifting field would make that something generate a magnetic response, a signal that Galileo could detect from orbit. And detect it did. As Galileo flew past Europa, its magnetometer picked up exactly such a response, a magnetic echo coming from within the moon, perfectly timed to the changing field of Jupiter. Europa was answering Jupiter's magnetism with a field of its own, and this immediately raised the question of what, inside a frozen moon, could possibly conduct electricity well enough to produce that echo. Solid ice will not do it. Cold rock will not do it. But there is one substance that conducts beautifully, a substance we know intimately on Earth, and that is salt water. A global layer of salty liquid water, an ocean rich in dissolved salts, is an excellent electrical conductor. The induced magnetic field that Galileo measured was just what you would expect from a salty sea sloshing beneath the ice. Let that settle for a moment, because this is the beam that holds up the whole structure. We did not just see a surface that looked like floating ice. We did not just calculate that there could be enough tidal heat to melt water. We detected, directly from orbit, the magnetic fingerprint of a conducting layer inside the moon. And the most natural explanation for that fingerprint is a global ocean of salt water. The surface clues and the magnetic evidence and the tidal heating all converged on a single answer. Beneath the bright ice of Europa, there is a sea, not a frozen ghost of one, a real liquid, salty, planet-wrapping ocean, kept warm from within, hidden under a roof of ice. And now let me give you the scale. Because the scale is what turns this from a curiosity into something staggering. The ice shell that caps this ocean is thought to be somewhere between 15 and 25 kilometers thick, which is to say roughly 10 to 15 miles of solid ice standing between the surface and the water below. That is a formidable roof. A barrier taller than the deepest trench in any earthly sea is deep. But beneath it, the ocean itself may run 60 miles deep, perhaps more, a black abyss of liquid water reaching down to the rocky heart of the moon. 60 miles. On Earth, the average depth of our oceans is only a couple of miles. Europa's hidden sea could be many times deeper than anything on our own world. And because Europa, though smaller than Earth, is covered by this ocean almost entirely, with no continents to break it up and a depth that dwarfs our own, the total amount of water it holds is almost beyond belief. The best estimates suggest that this single moon, this modest icy marble we ignored for centuries, contains roughly twice as much liquid water as all of Earth's oceans combined. Every sea on our planet, every gulf and bay and trench, all the water in all the oceans of the world, and Europa holds about double that, sealed in darkness beneath its ice. A small moon, a sea larger than all of ours together, hidden, silent, out of reach. It is worth holding that comparison in your mind for a moment longer, because the human imagination struggles with numbers this large and only really feels them through pictures. Picture every ocean you have ever known. The Pacific, so wide that it spans nearly half the planet. The Atlantic, with its great cold depths. The Indian Ocean, the Arctic, the Southern Ocean ringing the bottom of the world. Picture every sea and gulf and bay, every trench plunging miles into the dark, all the water that covers most of the surface of our world. Now, gather all of it together into a single quantity, the total water of Earth, and then double it. That doubled volume, that sea twice the size of all our seas, is what a single moon smaller than our own may be holding beneath its ice. The mind almost refuses it. A world we could cover with the palm of an outstretched hand against the night sky, holding more liquid water than the entire surface of the earth, and not frozen. Liquid, dark and salty and warm enough to flow, sealed beneath a roof of ice 10 to 15 miles thick. And consider what that ocean touches. Unlike the gas giant it orbits, Europa has a rocky heart, a core of stone at its center, and the deep ocean very likely rests directly against that rock. This matters enormously, because on Earth some of the most extraordinary life we know lives exactly at such a boundary, in the lightless depths of our own oceans where hot, mineral-rich water vents up from the rocky seafloor. There, in total darkness, with no sunlight reaching down, whole communities of living things thrive on the chemistry seeping out of the rock. If Europa's ocean meets its rocky floor in a similar way, then the same kind of chemistry, the same kind of energy that feeds life in the dark of our own deep sea, could in principle be available there too. The ocean would not be a sterile bath sealed off from everything. It would be a sea in contact with rock, where the ingredients and the energy for interesting chemistry might genuinely come together. And there, precisely, was the agony of it. We had built, beam by beam, an overwhelming case that the ocean was real. We had the heat, we had the surface, we had the magnetic echo. We were as confident as we could be that a vast sea turned slowly in the dark beneath that ice. And yet we could not touch it, we could not sample it, we could not see it. 10 to 15 miles of solid ice sealed it away from every instrument we had. We could infer the ocean, we could believe in it, but we could not read it. The water kept its secrets. Locked behind a frozen door we had no way to open. Think about what that sealing truly meant in practical terms, because it is easy to underestimate. 10 to 15 miles of solid ice is not a lid you lift. It is a barrier thicker than the deepest mine humanity has ever dug, thicker than the tallest mountains are tall. No drill we have ever built could reliably bore through it. No probe could be lowered down on a cable. Even if you somehow melted a path downward, the ice would close behind you, and the radiation at the surface and the crushing cold would fight you at every step. The ocean of Europa is not merely far away. It is armored, sealed behind a roof so thick that reaching it directly with any technology we possess would be one of the hardest engineering tasks ever attempted. For all our certainty that it was there, the water might as well have been locked in a vault with no door, a treasure we could prove existed but could not approach. The inference was strong, the reach was non-existent. And that gap between knowing and touching is one of the most frustrating places a scientist can stand, certain of a thing and utterly unable to confirm it by going there. For the question that mattered most was not simply whether the water existed, it was what the water contained. An ocean is just a place until you know its chemistry. Life as we understand it needs more than liquid water. It needs the right ingredients dissolved within that water, the elements and compounds from which living things are built, And above all, it needs carbon, the element at the heart of every organism we have ever known. So the real question, the one that kept the scientists awake, was this. Even if there is an ocean down there, is it a sterile bath of plain salt water, or is it a sea rich with the chemistry of life? And how, sealed beneath 15 miles of ice, could we ever possibly find out? That was the wall we had run into. Sit for a moment in the strangeness of that wall, because it is a peculiarly modern kind of frustration. We had used reason and instruments to become almost certain of something we could not see. We could describe the ocean's likely size, its saltiness, its depth, the thickness of its frozen roof. We could speak about it with real confidence. And yet between us and the actual water stood a barrier we had no means to cross. It is a little like knowing, with great certainty, that a sealed room exists behind a wall, knowing roughly its dimensions and what it likely holds, and being utterly unable to open the door or even drill a peephole through. The knowledge is real. The reach is absent. For an explorer, for a curious mind, there are few situations more maddening, and it was precisely this maddening gap that forced a change of approach. If we could not go down to the ocean, then perhaps we could persuade the ocean somehow to send a sign up to us. Perhaps we did not need to break through the ice at all. Perhaps we only needed a way to read whatever the moon was already, quietly, showing us on its surface. And to get past it, we would need a new kind of eye. A new kind of eye. That is what the problem demanded, and it is worth pausing to understand just how strange the solution turned out to be. Because we did not solve the puzzle of Europa's hidden chemistry by drilling through the ice, we did not send a submarine into the sealed sea. We did not even in this chapter of the story fly anything close to the moon at all. Instead, we read the ocean from across the solar system by catching the light that bounced off the surface of the ice and listening to what that light had to say. To understand how that is even possible, we have to talk about the most powerful telescope humanity has ever built, and about a quiet kind of magic called spectroscopy. The telescope is the James Webb Space Telescope, and most people, when they hear its name, picture beautiful photographs, glittering fields of galaxies, towering clouds of gas where stars are born, sweeping portraits of nebulae in colors no human eye could see. And Webb does produce those images, and they are glorious. But a photograph, however stunning, is in some sense the least of what this machine can do. Webb was not built mainly to take pretty pictures. It was built to read light, to take the faint glow arriving from a distant object and split it apart, color by color, and from that splitting to determine what the object is actually made of. Webb is, at its heart, a chemistry instrument. It is a machine for reading the composition of things impossibly far away. And that capability is what let us reach across more than 500 million miles and sample the surface of a frozen moon without ever going near it. To see how, you have to understand spectroscopy, and the easiest way in is through something everyone has seen: a rainbow. When sunlight passes through raindrops, the white light spreads out into a band of colors, red and orange through to blue and violet. What is happening is that white light was never truly one color at all. It is a blend of every color mixed together, and the raindrops simply separate the blend back into its parts. A device called a spectrograph does the same thing on purpose and with great precision. It takes a beam of light and spreads it into its full spectrum of colors, including the colors our eyes cannot see, the infrared light beyond red, and the ultraviolet beyond violet. And when you spread light out this finely, something extraordinary becomes visible. The spectrum is not perfectly smooth. It is crossed by dark lines, narrow gaps where particular colors are missing, as though someone had reached into the rainbow and plucked out specific threads. Those missing threads are the key to everything. Here is why they appear. When light passes through or bounces off a material, the atoms and molecules in that material absorb certain very specific colors and let the rest pass by untouched. Each kind of molecule absorbs its own unique set of colors, no two patterns quite alike. Water absorbs one set, carbon dioxide absorbs another, a simple salt absorbs yet another. So when you spread out the light that has interacted with a substance, and you see exactly which colors are missing, exactly where the dark gaps fall, you are reading a fingerprint. You are reading a barcode that tells you precisely which molecules the light has touched. This is spectroscopy, and it is one of the most powerful ideas in all of science. It means we can know what a thing is made of without ever holding it, without ever touching it, by light alone. Let me slow down here, because this idea is so powerful and so easy to take for granted that it deserves a second pass. For most of human history, there was a hard limit on what we could ever hope to know about the cosmos. You could measure where a star was and how bright it appeared, but its actual nature, what it was made of, seemed forever beyond reach. A famous thinker once declared that the chemical composition of the stars was a thing humanity would never know, a permanent boundary on knowledge, because we could never travel to a star and bring a piece of it home. And he was wrong, gloriously and completely wrong, and the thing that proved him wrong was spectroscopy. Within a few decades of that confident declaration, scientists were reading the chemistry of the sun and the stars from their light alone, finding the fingerprints of familiar elements in the dark gaps of their spectra. The boundary that was supposed to be permanent simply dissolved. We learned to read the makeup of objects we could never touch, written in shadow across their light. It remains, to my mind, one of the most quietly miraculous things our species has ever learnt to do. And the wonder of it is that the same trick works at every scale, on the largest and most distant things and on the small ones close to home. The light from a galaxy at the edge of the observable universe carries the same kind of fingerprints as the light reflecting off a moon in our own backyard. The physics does not care about distance. A molecule absorbs its particular colors whether it sits in a star 1,000 light years away or in a patch of frost a few 100 million miles off. So the moment we built an instrument sensitive enough and precise enough, the surface chemistry of Europa became readable in exactly the same way the chemistry of the stars had become readable 1.5 centuries before. The only thing standing between us and that knowledge was the instrument. We needed an eye sharp enough, cold enough, and far enough from the interference of our own warm world to catch those faint infrared fingerprints and read them cleanly. We needed Webb. This is how we know what distant stars are made of. Stars we will never visit. Suns trillions of miles away. We catch their light. We spread it into a spectrum. We read the missing colors, and the gaps tell us hydrogen, helium, carbon, iron, the whole recipe of a star written in shadow across a rainbow. And the same trick that reads a star can read a moon. Sunlight falls on Europa. It strikes the ice and the frost, and whatever chemistry coats the surface. Some of it is absorbed, color by color, according to what is there. The rest reflects back into space, carrying with it the dark fingerprints of every molecule it touched. If you could catch that reflected light and spread it finely enough, you could read the surface chemistry of Europa from a great distance. The only problem, for a very long time, was that no instrument was sensitive enough, sharp enough, and stable enough to do it well, especially in the infrared where the most interesting fingerprints lie. Until Webb. Let me give you a sense of what this telescope is, because its very existence is a kind of marvel. Its main mirror is not a single piece of glass, but a honeycomb of 18 hexagonal segments coated in a microscopically thin layer of pure gold, the whole array spanning more than 6 meters, far larger than any telescope mirror ever flown before. Gold, because gold reflects infrared light beautifully, and infrared is precisely the range Webb was built to see. The entire telescope is chilled to extraordinary cold, hundreds of degrees below freezing, shielded from the sun by a vast layered sunshade the size of a tennis court, because infrared light is heat, and a warm telescope would be blinded by its own glow the way you cannot see stars under a streetlight. To keep it that cold and that still, Webb does not orbit close to Earth. It sits roughly 1 million miles away, 4 times farther than the Moon, at a special balance point in space where it can hold steady and stare into the dark. From that distant perch, it can gather the faintest threads of infrared light from across the universe and read them with a precision nothing before it could match. Building such a machine was itself an act of almost reckless ambition, and it is worth remembering as a measure of what we are willing to attempt. Webb took decades to design and build, cost a fortune, and depended on hundreds of mechanisms that all had to work perfectly the first time, with no possibility of repair. Unlike telescopes that orbit close to Earth, Webb sits 1 million miles away, far beyond the reach of any astronaut, so if anything had gone wrong during its unfolding, there would have been no rescue. And a great deal had to go right. The mirror had to be folded to fit inside a rocket, and then unfold in space with perfect precision. The vast sunshield had to deploy in delicate layers without tearing. Hundreds of single points of possible failure had to each succeed in turn, in the cold and the dark, with the whole watching world holding its breath. And it worked. Every step unfolded as it was meant to, and the great gold eye opened in the silence 1 million miles from home. That such a thing was even attempted, let alone achieved, tells you something about the strange creatures we are, willing to stake decades of work and a fortune of treasure on a machine flung beyond all hope of repair, simply to see more clearly. And the reward for that audacity was the power to read the chemistry of the cosmos, including, when we chose to point it homeward, the frost on a hidden ocean moon. And one day, in late 2022, this machine built to study the first galaxies that ever formed, this instrument designed to look back toward the dawn of cosmic time, turned its golden eye inward. It looked not outward to the edge of everything, but homeward, across our own solar system, and it pointed itself at Europa. The instrument it used is called NIRSPEC, the Near-Infrared Spectrograph, and it does exactly what its name promises. It takes infrared light and spreads it into a spectrum, reading the chemical fingerprints hidden in the missing colors. But NIRSPEC has a further gift that matters enormously for this story. It does not merely read the chemistry of an object as a single blurred whole. It can build a map. It can take a spectrum from many different spots across the face of the moon and stitch them together, so that instead of one answer for all of Europa, you get a picture of where each chemical lives. This molecule concentrated here, that one spread there. It does not just tell you what is present, it tells you where. Sit with how astonishing that is. Europa, when Webb observed it, was on the order of 600 million miles from Earth, a distance so vast that light itself, the fastest thing there is, takes the better part of an hour to cross it. The moon appeared in Webb's view as a tiny disk, a small bright coin against the black. And yet from that coin, from the trickle of sunlight it reflected back across the immensity of space, Webb could pull apart the colors finely enough to read the frosts on its surface and to map where on that distant face the different chemistry lay. We were, in effect, performing chemistry on a frozen ocean world without leaving home, reading the composition of its skin by light that had bounced off ice 10 to 15 miles above a sea no instrument had ever sampled. The reach of it borders on the unbelievable. A telescope built to see the beginning of the universe, pausing to read the frost on a moon next door. So Webb gathered its light, and NIRSpec spread it into spectra across the face of Europa, and the scientists waited for the dark fingerprints to resolve out of the data. And as the spectrum came together, one signature stood out, clear and unmistakable in the pattern of missing colors: carbon dioxide. The molecule of carbon bound to oxygen, the same gas you exhale with every breath, the same gas that bubbles in sparkling water and hangs in Earth's atmosphere. There it was, written into the infrared light reflecting off the surface of Europa. Carbon dioxide, frozen onto the ice of a distant moon, detected from across the solar system by the faint colors it had quietly absorbed. Now, on its own, the simple presence of carbon dioxide might not seem like the kind of revelation that changes our view of a world. Carbon dioxide is common. It drifts through space in countless forms. It frosts onto cold surfaces all over the solar system. Finding it on Europa, taken alone, could mean any number of things. It might have been delivered from outside, dropped onto the moon by comets and meteorites that carried carbon across the void and splattered it onto the ice. It might have been manufactured right at the surface, cooked up by the relentless radiation that pours down onto Europa from Jupiter's fierce magnetic environment. Radiation capable of breaking apart molecules and reassembling them into new ones. Or it might have come from somewhere far more interesting. It might have risen from below. It might have been carried up from the hidden ocean itself, a sample of the sea's own chemistry delivered to the surface where, at last, a telescope could read it. 3 possibilities. Delivered from space, made at the surface, risen from the deep. From the outside they can look the same, a frost of carbon dioxide on the ice either way. The simple fact that the molecule was there did not, by itself, tell us which story was true. And the difference between those stories is the difference between a curiosity and a discovery that reshapes our sense of where life might be. If the carbon came from comets or from radiation, it tells us little about the sea below. But if the carbon rose from the ocean, then for the first time we would be holding in our hands, or rather reading in our light, a genuine sample of the chemistry of that hidden water. We would know that the sea contains carbon, the very element from which all life as we know it is built. It is a strange and humbling situation to find yourself in. As a scientist, you have made a genuine discovery. You have detected carbon dioxide on the surface of an ocean moon, a real and solid finding read cleanly from the light. And yet the discovery, instead of settling anything, has handed you a sharper question than the one you started with. This is how science so often actually moves, not from question to answer to rest, but from question to answer to a better question. The carbon dioxide was real. Where it came from was now the mystery, and the stakes of that mystery were enormous, because the answer would decide whether Webb had merely found another frost on another moon, or had, for the first time in history, read a sample of a hidden alien ocean from across the solar system. And here the genius of NIRSpec, the thing that set it apart from every instrument that had studied Europa before, became the key to everything. Because NIRSpec had not returned a single blurred answer for the whole moon, it had returned a map. It knew not just that carbon dioxide was present, but where on the face of Europa it was concentrated and where it was sparse. And that map, that knowledge of location, was about to become the deciding evidence. For the three competing stories about the carbon, delivery from space, manufacture by radiation, and rising from the ocean, each made a different, quiet prediction about where the carbon should be found. The scientists did not have to guess between the stories. They could lay Webb's map against those predictions and see which one the data actually matched. The answer was waiting in the distribution, in the simple question of where the carbon lived. So the discovery of carbon dioxide was not the end of the story. It was the beginning of a question, and the question was as sharp as any in planetary science. Where did this carbon come from? Was it a visitor from space, a surface trick of radiation, or a message from the deep? Everything hinged on the answer. And to find that answer, the scientists did not need to fly anywhere new. They already had the data. They had Webb's map. They had the one thing NIRSpec could provide that nothing before it could. The knowledge not just of what was there, but of exactly where on the moon's face the carbon dioxide was concentrated. There is a beautiful economy in that when you sit with it. We had been agonizing over a sealed ocean we could not reach, a sea locked behind miles of ice with no door, and it turned out that we did not need to break the door down at all. The moon had, in a sense, slipped a note out under it, a trace of its inner chemistry carried up to the surface and laid on the ice where reflected sunlight could catch it and bring it to us. We did not have to drill. We did not have to dive. We only had to be patient enough and clever enough to read what the moon was already showing us, and then to ask the one further question that would unlock its meaning. And when they looked at where the carbon lived, the location itself would turn out to tell the whole story. When the scientists looked at where the carbon lived, the map did something maps rarely do. It answered the question almost by itself. The carbon dioxide was not spread evenly across Europa. It was not scattered uniformly the way a steady rain of comet debris would scatter it, nor smeared across the whole sunlit face the way surface radiation chemistry might smear it. Instead, it was gathered, concentrated, pooled into one particular region of the moon, and that region had a name, and the name turns out to matter more than almost anything else in this entire story. The region is called Terra Regio, and Terra Regio is chaos terrain. Let me bring you down to that place, because it is the heart of everything. Remember the chaos terrain from earlier, those zones where the smooth ice is broken into a jumbled mosaic of tilted slabs and rafted blocks, the places that look as though the crust was shattered, set adrift, and refrozen. Terra Regio is exactly such a place. It is a scarred and disrupted patch of Europa's surface, geologically young, torn up and resurfaced, a region where the ice has not sat quietly for ages, but has been broken and reworked in the relatively recent past. It is, in other words, one of the places on the entire moon where the surface and the interior are most likely to have been in contact, where material from below could have been brought up, where the sealed door between the surface and the sea is, if it is anywhere, most likely to have been cracked open. And it was precisely here, in this broken and active terrain, that Webb found the carbon dioxide concentrated, not in the old, undisturbed, quiet ice, not spread at random across the globe, but pooled in the one kind of place where the ocean below and the surface above could plausibly have exchanged material. The location was not incidental. The location was the clue, because if the carbon had simply rained down from space, there would be no reason for it to prefer the chaos terrain over any other patch of ice. Comets and meteorites do not aim for the geologically interesting regions. They fall everywhere, indifferent to the landscape beneath them. A carbon dioxide delivered from outside should be smeared more or less evenly across the moon, with no special love for Terra Regio. But that is not what Webb saw. Webb saw the carbon gathered exactly where the deep ocean was most likely to have touched the surface. The first alternative, delivery from space, began to crumble. What about the second possibility, that the carbon was manufactured at the surface by Jupiter's radiation? This one took more care to rule out, because Europa truly is bathed in radiation, and that radiation truly can drive chemistry, breaking molecules apart and welding the pieces into new compounds. It is a real process, and the scientists took it seriously. But again, the distribution argues against it as the main source. Radiation pours down across the whole sunward face of the moon, and the chemistry it drives should reflect that broad exposure, not concentrate itself so tightly in one disrupted region. More than that, when researchers examined the carbon dioxide closely, they found it associated with the chaos terrain in a way that fit an origin from within far better than an origin from surface processing alone. The carbon was behaving like something that had come up from below and been deposited where the crust was broken, not like something cooked uniformly into the ice by radiation from above. The second alternative weakened too, which left the third possibility, the one that had seemed almost too much to hope for, that the carbon had risen from the ocean, that it was a genuine sample of the chemistry of the hidden sea, carried up through the broken ice of the chaos terrain and laid down on the surface where, at last, a telescope 1,000,000 miles from Earth could read it in reflected light. And as the alternatives fell away, this was the explanation left standing, the one the evidence pointed toward. The carbon dioxide on Europa appears to come from inside the moon, from the water, from the deep. Let me make the logic of that distribution as plain as I can, because it is the spine of the whole discovery, and it rewards a careful look. Imagine 3 painters, each told to cover a globe with paint, but each working by a different rule. The first painter is space itself, the slow rain of comets and meteorites carrying carbon from outside. This painter is blind to the landscape below. It splatters its paint at random, a little here, a little there, with no preference for any region, because a falling comet does not know or care whether the patch of ice beneath it is old smooth crust or young broken chaos. If this painter were responsible, the carbon dioxide would be smeared more or less evenly across the whole moon, indifferent to the terrain. The second painter is radiation, the steady downpour of charged particles from Jupiter that drives chemistry on the surface. This painter works across the entire sunward face, broadly, wherever its particles can reach, and so it too would tend to spread its product widely rather than concentrate it in one small disrupted region. But the third painter is the ocean itself, reaching up through the cracks and weaknesses of the broken ice, depositing its carbon only where the crust has been torn and reworked enough to let material through. This painter would paint precisely one kind of place, the chaos terrain, the young, disrupted, resurfaced ground where the deep has touched the surface. Now look again at what Webb actually saw. The carbon was not smeared evenly, as the first painter would have left it. It was not spread broadly across the sunward face, as the second painter would have left it. It was concentrated tightly in terra regio, in the chaos terrain, in exactly the kind of place, and only the kind of place that the third painter, the ocean, would have chosen. The map matched the prediction of an internal source and contradicted the predictions of the external ones. This is what it means to do detective work across 500 million miles of empty space. You cannot visit the scene. You cannot interview the witness. But you can ask each suspect where the evidence should fall if they were guilty, and then you can look at where the evidence actually fell and let the location speak. The location spoke clearly. It pointed down, into the moon, toward the sea. But the scientists did not rest the case on location alone. There was another thread to pull, finer and more technical, and it runs through the very atoms of the carbon itself. Carbon comes in slightly different versions, called isotopes, atoms that are chemically the same but carry a little more or a little less weight in their cores. The two that matter here are the common, lighter form and a rarer, heavier form. The ratio between them, how much of the heavy kind there is compared to the light kind, acts like a subtle signature, and that signature can hint at where a substance came from and how it formed. Carbon delivered fresh from certain kinds of space debris can carry one balance of isotopes. Carbon that has cycled through the chemistry of a planetary interior can carry another. By reading the spectrum carefully, Webb could begin to measure this balance for the carbon dioxide on Europa, and the value they found was consistent with carbon sourced from within the moon rather than delivered from outside. It was not a surface accident. It was not, on the best reading of the data, a gift from passing comets. It carried the mark of having come from inside Europa, from the world beneath the ice. Pull these threads together and feel the weight of what they form. The carbon dioxide is concentrated in the chaos terrain, exactly where the ocean and surface could meet. Its distribution does not fit delivery from space. Its distribution does not fit manufacture by surface radiation as the main source. And the isotopic signature of the carbon itself is consistent with an internal origin. Every line of evidence converges on a single conclusion, and it is a conclusion worth saying slowly and plainly. We are very likely reading the chemistry of Europa's hidden ocean, written onto the surface of its ice, from across the solar system. For the first time, we have what looks like a genuine sample of that sealed and silent sea, and the sample contains carbon. I want to make sure the meaning of that lands, because it is easy to hear carbon and move on. Carbon is not just another element on the list. Carbon is the element. Every living thing we have ever found, every plant and animal and microbe, every cell that has ever divided on the surface of the earth is built on a framework of carbon. Carbon is the atom uniquely able to link itself into long chains and rings and lattices to form the vast and intricate molecules that life requires, the proteins and sugars and the spiral of genetic code. When we search the universe for life, we are, at bottom, searching for carbon chemistry in the presence of liquid water and a source of energy. Those are the three pillars: liquid water, energy, and carbon. And look at what Europa now offers. We already had strong evidence of the water, a global ocean perhaps twice the volume of all Earth's seas, kept liquid beneath the ice. We already had the energy, the ceaseless tidal heating from Jupiter's gravity, a furnace burning in the dark that needs no sunlight at all. And now, with Webb, we have evidence of the third pillar. Carbon, apparently present in that ocean, rising through the broken ice to be read in reflected light. Water, energy, carbon, the three things that, on Earth, came together to produce life. All three, it now seems, are present in the hidden sea of a frozen moon we spent centuries dismissing as a dead ball of ice. And there is a poetry in the particular way this carbon reached us that I do not want to pass over. Think of the journey it made. It began, most likely, dissolved in the dark water of the ocean far below, where no light has ever fallen. Somehow, through the slow churning of that sea and the breaking and healing of the ice above it, it was carried upward, through cracks and weaknesses in the chaos terrain, until it reached the surface and froze there as carbon dioxide on the bright skin of the moon. And there it sat, on the sunlit ice, for who knows how long. Then sunlight, having travelled 8 minutes from our own star out to Jupiter, struck that frozen carbon, and a fraction of that light, carrying now the dark fingerprint of the carbon it had touched, bounced back out into space and travelled the better part of an hour across the void to fall, at last, into the gold mirror of a telescope 1,000,000 miles from Earth. From the lightless deep of an alien ocean, up through miles of ice, onto a sunlit surface, and then across 600 million miles of empty space into our waiting instrument. That is the path this single message took, and we were clever enough, and patient enough, and curious enough to be standing at the end of it, ready to read what it said. I am not telling you there is life on Europa. No one is. That is not what this discovery shows, and it is important to be honest about exactly where the line falls. Webb did not find organisms. It did not find biology. It did not even directly sample the ocean. What it found is that the chemistry is right, that the ingredients we associate with the possibility of life appear to be present, that the sea down there is very likely not a sterile bath of plain salt water, but a chemically rich ocean carrying carbon. The discovery does not answer the great question. It does something almost more thrilling. It makes the question reasonable. It moves Europa from a place where we hoped life might conceivably be possible to a place where the basic conditions for life appear, as far as we can tell from a great distance, to actually be met. It turns a long shot into a genuine candidate. And in the careful, patient world of planetary science, that shift from conceivable to plausible, from hoped for to evidenced, is enormous. It is the difference between a daydream and a destination. And there is a further wrinkle to the story, a development that came as scientists kept looking that makes the picture even more compelling. The first detection found the carbon concentrated in Terra Regio, but Terra Regio is not the only chaos terrain on Europa. As researchers continued to study the Moon with Webb, they found that the link between carbon dioxide and disrupted terrain was not a one-off coincidence of a single region. The carbon appeared to be associated with chaos terrains more broadly, with the scarred and reworked patches of crust scattered across the Moon, tracking the very regions where the surface texture hints at exchange with the layers below. This is exactly what you would expect if the carbon is coming up from inside. It is not tied to one special spot that might be explained away as a fluke. It follows the geology. It appears where the ice has been broken and renewed, again and again, as though the Moon were quietly marking for us every place where its hidden sea has pressed up toward the light. The pattern repeats, and a pattern that repeats is a pattern you can trust. Step back and feel the shape of what has happened. We began with a Moon we called dead. We reasoned our way to a hidden ocean we could not touch. And now, without drilling a single inch into the ice, we have evidence that the ocean carries carbon, the signature ingredient of life, and that this carbon is rising up through the broken places in the crust where the deep meets the surface. We have gone from a frozen billiard ball to a sealed sea to a sea whose chemistry we are beginning to read, and we have done it all from a distance that light itself takes the better part of an hour to cross. Each step would have seemed impossible to the people standing at the step before. The astronomers who first resolved Europa's smooth face could not have dreamed we would one day infer its ocean. The scientists who inferred the ocean could not have dreamed we would one day read its carbon from home. And we, today, reading its carbon from home, can only begin to dream of what the next step will reveal. And consider what it took to learn this. We did not drill, we did not land, we did not pierce the ice or dive into the water. We caught sunlight that had bounced off the frost of a moon 600 million miles away, spread that light into its colors, read the dark fingerprints in the missing threads, mapped where on the distant face the carbon lived, and from the location and the isotopes alone, reconstructed a story that reaches all the way down through 15 miles of ice into a sea no eye has ever seen. The ocean is sealed, the door is shut, and still, through nothing but light and patience and the cleverness of reading chemistry from a rainbow, we have begun to read what that ocean contains. A carbon-bearing sea, turning slowly in the dark, with everything it would need to be more than just water. But reading the chemistry from afar, however astonishing, is not the same as going there. Webb has shown us the fingerprint on the door. It has told us, as much as any telescope can, that something worth finding lies behind it. What it cannot do is open the door. It cannot measure how thick the ice truly is, cannot taste the water, cannot map the chaos terrain in the fine detail that would let us see where and how the ocean breaks through. And so the story arrives at a natural turning point, the moment where reading gives way to reaching. Webb did something almost magical, pulling the chemistry of a hidden ocean out of a smear of reflected light across 500 million miles of space. But there is a ceiling to what light alone can tell you from that far away. Webb could say carbon is here, concentrated in the broken ground, likely risen from below. It could not say how thick the ice truly is at that spot, or whether the ocean reaches the rock beneath, or what else the water holds beyond carbon, or whether anything down there is stirring. To answer those questions, you cannot squint harder from 1,000,000 miles away. You have to close the distance. You have to send a machine across the dark to fly close to the ice and measure the moon directly with instruments that touch what light alone could only hint at. For that, you cannot stay home and read reflected light. For that, you have to go. And the remarkable thing, the thing that turns this from a story about the past into a story about the very near future, is that we already have. The journey to confirm what Webb glimpsed is not a proposal or a dream. It is underway. A spacecraft is crossing the dark toward Europa right now. On a morning in October of 2024, on the coast of Florida, one of the most powerful rockets in the world stood fueled and waiting on its launch pad. Perched at its top, wrapped in a protective shroud, sat the largest spacecraft NASA has ever built for a mission to another planet. Its name is Europa Clipper, and its single purpose is to answer the question that everything in this story has been building toward. Is the hidden ocean of Europa truly a place where life could exist? When the engines lit and the rocket climbed into the sky and let go of its precious cargo, humanity did something quietly historic. We sent a dedicated mission to study an ocean world beyond Earth for the very first time. Not a flyby on its way somewhere else, not a side glance from a passing probe, a spacecraft built from the ground up to investigate a sea on another world. There is a detail about the launch that I find quietly beautiful, and it speaks to the spirit of the whole endeavor. Tucked aboard the spacecraft, etched and engraved, Clipper carries messages from Earth, including the names of millions of people who signed on to send their names to Europa, and a poem written for the occasion, and a plate honoring the human longing to understand other worlds. It is not science, exactly. It will gather no data, but it says something about why we do this at all. We did not build and launch the largest planetary spacecraft in our history purely to measure the thickness of ice. We did it because something in us cannot bear to leave the question unanswered, cannot look up at that bright point beside Jupiter and simply accept that we will never know what lies beneath its frozen skin. The names and the poem riding along in the dark are a reminder that this is, underneath all the engineering, a deeply human act, a reaching, a refusal to stay ignorant of a sea we have every reason to believe is there. Europa Clipper is enormous, and it has to be. When its solar panels are unfolded, the spacecraft stretches more than 100 feet from wingtip to wingtip, wider than a basketball court, because out at Jupiter sunlight is faint, and you need vast wings to gather enough of it to run your instruments. Those great solar arrays make Clipper the largest spacecraft NASA has ever developed for a planetary mission. A machine the size of a small bus trailing wings the length of a house, sailing now through the emptiness between the planets. And at its heart, shielded and armored, sits a suite of scientific instruments more capable than anything we have ever flown to the outer solar system, each one chosen to reach toward the ocean in a different way. The journey is long, and the length of it teaches a kind of patience that our instant world rarely asks of us. Europa is not next door in any human sense. Even at the speed of a rocket, you cannot simply fly straight there. Clipper will travel something like 1.8 billion miles to reach Jupiter, looping first through the inner solar system to steal momentum from the gravity of other worlds, swinging past Mars and then back past Earth, each close pass flinging it a little faster and farther, like a stone whirled on a lengthening string before release. It will not arrive until around the year 2030. More than 5 years of travel through the dark for a mission that has been dreamed about and argued over and designed and redesigned for decades before that. The people who first imagined a spacecraft like this are, some of them, no longer alive to see it fly. This is science on the scale of a human lifetime, a relay of patience handed from one generation to the next. It is worth sitting with that patience for a moment, because it runs against everything the modern world trains us to expect. We live in an age of immediacy, of answers arriving the instant we ask for them, of distances collapsed by screens. And here is a project that asks the opposite of us. The scientists who will guide Clipper through its closest and most delicate observations are working today on a spacecraft that will not deliver its most important results for years yet, results that will then take more years to fully understand. Some of the engineers who designed its instruments began this work in the prime of their careers and will be near the end of them before the data comes home. Children who are not yet born will be in school when Clipper sends back its measurements of the ice. There is something deeply moving in that, a willingness to begin work whose harvest you may only partly live to see, to plant a question in the dark and trust that the answer will arrive in its own slow time. It is the opposite of impatience. It is a kind of faith in the future, expressed in metal and fuel and code, flung across 2 billion miles of nothing. And when Clipper finally reaches Jupiter, it will face an enemy that makes the whole endeavor extraordinarily difficult. Jupiter is wrapped not only in a magnetic field, but in belts of radiation so intense they would kill a human being in moments and can fry the delicate electronics of a spacecraft in short order. Europa orbits within reach of these brutal belts, swimming through a storm of charged particles. To survive long enough to do its work, Clipper carries its most sensitive electronics inside a thick vault, a shielded box with walls of metal built to absorb the worst of the radiation and protect the brain of the spacecraft within. And rather than settling into a low orbit around Europa, where it would be bathed continuously in that lethal radiation and quickly destroyed, Clipper will do something cleverer. It will orbit Jupiter itself on a wide looping path and dart in close to Europa only for brief flybys, dozens of them across the mission, each one a quick dive past the moon to gather data before swinging back out to the relative safety of the larger orbit. It will visit Europa again and again across the mission, like a careful diver surfacing between descents to breathe, building up its portrait of the moon flyby by flyby, while limiting how much radiation it has to endure at any one time. It is a clever compromise between the closeness the science demands and the survival the radiation threatens, and it lets a fragile machine do long work in a place that wants to destroy it quickly. So what will it actually do once it is there skimming above the ice? Think of its instruments as a set of different senses, each reaching toward the ocean in its own way. It carries ice-penetrating radar, a system that can send radio waves down into the ice shell and listen for the echoes that bounce back from layers and boundaries within, and crucially from the place where ice may meet water. With it, Clipper may be able to measure how thick the ice truly is, to test directly whether the shell is the 15 to 25 kilometers we have estimated, and perhaps even to glimpse pockets of liquid water trapped within the ice or the top of the ocean itself. After all our inference, all our argument from magnetism and surface clues, this radar could let us, in a sense, see into the ice for the first time. It carries cameras and spectrometers far more powerful at close range than any telescope peering from afar. Instruments that will map the chaos terrain in exquisite detail, resolving features far too small for Webb to make out from across the solar system. Where Webb saw Tara Regio as a smudge of concentrated carbon on a tiny disk, Clipper will fly close enough to map its broken slabs and ridges and the chemistry painted across them with a sharpness that turns a hint into a landscape. Picture for a moment what that radar reaching could mean. For all the certainty we have built about the ocean, no instrument has ever actually seen the boundary where ice gives way to water. We have inferred it from magnetism and from the behavior of the surface, but no one has ever measured directly how far down the water begins. Clipper's radar could give us that number at last, could send its pulses down through the shell and catch the echo from the ocean's roof. And in that echo we would have, for the first time, a direct measurement of the very thing this whole story has circled around. The 15 to 25 kilometers we have estimated would become a measured depth, or it would be revised. And either way, we would finally know the true thickness of the door that has kept the sea sealed away. There is something almost vertiginous in imagining it, a number arriving from across 2 billion miles that tells us precisely how deep the ice goes before the water begins. It carries instruments to study the thin wisps of gas around Europa and to analyze any plumes, any geysers of water vapor that might erupt from cracks in the ice and vent material from below directly into space. For if Europa does spout plumes, and there have been tantalizing signs that it might, then a spacecraft could fly straight through one and taste the ocean directly, sampling the spray of a hidden sea without ever having to drill. It carries a magnetometer of its own, a finer instrument than Galileo's, to measure the moon's magnetic response with new precision and pin down the depth and saltiness of the ocean below. Every instrument is another way of reaching toward the water. Every one is a different question asked of the ice. And the possibility of plumes deserves a moment of its own, because it would change everything about how directly we could touch the ocean. The dream, the thing that makes scientists lean forward when they talk about it, is that Europa might be venting its sea into space. If cracks in the ice open under the right stresses, water from below could rush up and erupt as towering fountains of vapor and ice, just as we have already watched happen on Saturn's moon Enceladus. And if Europa does this, even occasionally, then Clipper would not have to drill or melt or wait. It could simply fly straight through the spray, opening its instruments to the falling mist, and sample the ocean directly, tasting the chemistry of a sealed alien sea by catching its fountain in mid-air. There have been tantalizing hints that such plumes may exist, glimpses that are not yet certain, and one of the quiet hopes riding along with Clipper is that it might catch the moon in the act, might fly through a breath of the hidden ocean and read it molecule by molecule, to sample a sea sealed under 15 miles of ice, not by going down to it, but by catching the part of it that leaps up to meet you. It would be one of the most elegant pieces of exploration we have ever managed. But I have to be honest with you about what Clipper is and what it is not, because the distinction is important and it is easy to get carried away. Europa Clipper is not a life detection mission. It is not flying out there to find fish or microbes, or to send back a photograph of something swimming in the dark. It carries no instrument designed to definitively prove that life exists. What it is, in the careful language of the scientists, is a habitability mission. Its job is not to answer the question, is there life on Europa? But the question that must come first, could there be? Is the ocean really there? How thick is the ice? Is the water in contact with a rocky seafloor where useful chemistry could happen? Are the ingredients and the energy and the conditions truly suitable for life as we understand it? Clipper is sent to determine whether Europa is a place where life could exist, to map the habitability of that hidden sea in detail, and so to lay the groundwork for some future mission not yet built, that might one day go further and actually search for life itself. And think of how beautifully Clipper and Webb complete each other. The telescope and the traveler, two utterly different ways of reaching the same hidden sea. Webb stayed home and read the moon in reflected light, gathering the chemistry of the whole face at once, but seeing it only as a tiny distant disk, unable to resolve the fine detail or to know how deep the ocean lay beneath any given patch of ice. Clipper will do the opposite. It will see almost nothing of Europa from afar, but it will fly close again and again. And where Webb saw a smudge, it will see a world, mapping the chaos terrain ridge by ridge, sounding the ice with radar, tasting the thin gas around the moon, measuring the magnetic echo with a precision Galileo could only approach. Webb gave us the broad chemical portrait and the crucial clue that carbon rises from below. Clipper will give us the depth and the structure and the close detail, the ground truth that a telescope can never provide. Neither could answer the question alone. Together they form something like a complete method, the distant eye and the close hand, the reading of light and the measuring of the thing itself. This is how we actually come to know a world we cannot stand upon, not in one heroic stroke, but through many instruments and many years, each filling in what the others cannot reach. There is a kind of wisdom in that restraint, and a kind of honesty too. We do not leap straight to the most dramatic question. We build toward it, carefully, one confirmed fact at a time, the same way we built the case for the ocean itself, beam by beam. First we inferred the water, then Webb read the carbon. Now Clipper will go to measure the ice and the chemistry and the conditions up close. Each step earns the next. And if Clipper finds what many scientists suspect it will find, an ocean confirmed, an ice shell measured, a chemistry rich and promising and in contact with rock, then the case for sending a mission that could truly hunt for life becomes almost impossible to refuse. Clipper is not the end of the journey to Europa's ocean. It is the bridge. It is the mission that turns a glimpsed possibility into a measured reality and clears the way for everything that might come after. It is worth understanding why we proceed this way, in careful steps rather than one grand leap, because at first it can feel almost timid. Why not simply build the mission that lands and drills and searches directly for life and skip the patient middle step? The answer is that you cannot design a good life hunting mission until you know what you are hunting in. You need to know how thick the ice is to know whether you could ever get through it. You need to know where the ocean comes closest to the surface to know where to aim. You need to know the chemistry of the place, the temperatures, the radiation, the structure of the shell, before you can build instruments suited to find life there, rather than instruments that would be useless or blind. Clipper is the mission that draws the map for everything that might follow. It is the scout sent ahead to learn the lay of the land, so that whoever comes after, with whatever bolder mission we someday build, arrives knowing where to look and what to bring. There is no wasted motion in this. Each step is the foundation the next one stands on, and when you step back from the technical detail of volts and radar and flybys, what remains is something close to wonder. Consider the sheer thread of human intention stretched across the dark. Centuries ago we saw Europa only as a moving point of light. Then we learned to see its smooth, scarred face. We reasoned our way to a hidden ocean we could not touch. We built a telescope to study the birth of the universe and turned it homeward to read carbon on a moon's frost. And then we built a machine the size of a bus with wings like a house, packed it with instruments, armored it against radiation that could kill a person in minutes, and flung it on a 5-year journey across nearly 2 billion miles of nothing, all to fly close to one small icy world and ask whether the sea beneath its ice could hold life. Right now, as you listen, that machine is out there in the silence between the planets, falling toward Jupiter, carrying our oldest question toward one of the most promising places we have ever found to ask it. There is a thread here that stretches across centuries and refuses to break. It runs from Galileo squinting through his crude lens at 4 points of light beside Jupiter, to the Voyagers racing past with their cameras, to Galileo the spacecraft listening for a magnetic echo, to Webb reading carbon in reflected light, and now to Clipper falling through the dark toward the ice. Each generation handed the question to the next, a little sharper, a little closer to an answer, none of them able to finish it alone. We are simply the ones holding the thread now, in our turn, as it pulls taut toward Europa. It will arrive around 2030. Somewhere in the patient dark, it is already on its way. So let us pull back now, slowly, the way you pull back from a dream as it ends, and take in the whole of what we have found. A small moon, far from the sun, wrapped in ice. Beneath that ice, a sea larger than all the oceans of Earth combined, turning in total darkness, warmed not by any sun but by the patient squeezing of a giant planet's gravity. And rising through the broken ice of that sea, a thread of carbon, faint and quiet, caught from 600 million miles away by a telescope reading the colors of reflected light. Water, energy, carbon, the 3 pillars of life as we know it, assembled in the cold and the black, beneath a sky of ice, with no sun, no surface, no witness. That is the picture we have built tonight, layer by layer, and it deserves a moment of stillness before we let it go. Notice how far we have traveled from where we started. We opened with a comfortable belief that life is rare and distant, and that the search for it must reach across impossible gulfs toward other stars. And piece by piece, beneath the ice of a moon we had written off, that belief has been quietly dismantled and rebuilt at a grander scale. We found a sea where there should have been only frozen rock. We found warmth where there should have been only cold. We found carbon where there should have been only barren ice. And we found it all not light years away, but in our own solar system, on a world close enough that a spacecraft is already falling toward it. The thing we assumed was a search across the cosmos has turned out, at least in part, to be a search in our own backyard, among the icy moons we had barely bothered to glance at. The universe did not become smaller as we learnt this. It became larger and stranger and far more full of possibility, than the tidy story we began with ever allowed. Think about where this leaves the old story we began with, the comfortable belief that life is a thin green film clinging to one warm planet, and that to find it anywhere else we must look across impossible distances to other stars. That story assumed that life needs what Earth has: sunlight, a warm surface, a sky and a sea open to the light. But Europa offers a different and stranger possibility. It suggests that the ingredients for life might assemble in places utterly unlike our own, in darkness rather than light, beneath ice rather than open sky, warmed from within rather than from above. If life could begin in a sunless ocean sealed under miles of ice, then the universe is not the barren and hostile place it can seem. Then the warm lit surfaces we always assumed were necessary are only one kind of cradle among many, and the hidden dark oceans, which may be far more common than Earth-like worlds, become possible cradles too. There may be more of these sealed seas in our galaxy than there are planets like ours. The search for life may not be a search outward toward distant suns at all. It may be a search inward into the dark interiors of frozen worlds, beginning right here in our own solar system. And there is a strange comfort in considering how such a sea might work, how life, if it exists there, would have to live. On Earth, almost everything depends in the end on sunlight. Plants drink the light and turn it into food, and the animals eat the plants, and so the energy of our star flows up through the whole living world. But in Europa's ocean there is no sun, no light at all, only perpetual dark. Any life there would have to feed on something else, and the most likely something is chemistry, the energy locked in the minerals and compounds where the water meets the rocky floor, or carried down from the surface where radiation has stocked the ice with reactive ingredients. We know this is possible because we have seen it at home. In the deepest trenches of our own oceans, far below where any sunlight reaches, there are places where hot water rich in minerals pours up from cracks in the sea floor, and around those vents whole worlds of life flourish in the total dark, feeding not on sunlight but on the chemistry of the rock. Strange tube worms, pale crabs, mats of microbes, an entire thriving community living off the energy of the earth itself rather than the energy of the sun. If life can do that here, in the lightless deep of our own world, then perhaps it can do that there too, in the lightless deep of Europa. The dark is not necessarily empty. The dark, on Earth at least, turned out to be full, and there is a humility in that, a gentle correction of our pride, which I think is the most beautiful part of the whole story. We spent centuries looking past Europa. We called it a frozen billiard ball, a dead marble of ice, a place of no great interest. We aimed our grandest hopes at distant Earth like planets around other stars, worlds we cannot reach and may never reach. And all the while, one of the most promising places to look for life beyond our own was right next door, a moon we could see through a backyard telescope, hiding an ocean beneath its skin. The thing we were looking for, or at least the conditions for it, may have been close to home the entire time, waiting quietly in the dark while we stared past it toward the far horizon. How often, I wonder, is that true of the things we search for? How often is the remarkable thing not in the distance, but nearby, overlooked precisely because it was close, dismissed because it was familiar, waiting patiently to be seen? Let me say a little more about why these dark oceans may be so common, because it deepens the wonder rather than dispelling it. Europa is not alone. It is only the nearest example of what appears to be a whole category of worlds. Out at Saturn there is a small moon called Enceladus, and we have already watched it spray fountains of water vapor and ice into space from cracks near its south pole, plumes that almost certainly come from a hidden ocean beneath its own ice. Saturn's giant moon Titan may hide a sea of water far below its surface as well. Ganymede, the largest moon of Jupiter, the largest moon in the entire solar system, shows its own magnetic signs of a buried ocean. Even distant Pluto, far out in the cold edge of everything, may hold liquid water deep within. Once you learn to recognize the signs, these hidden oceans begin to appear everywhere you look in the outer solar system, sealed inside icy moons, kept warm by tides and by the slow heat of their own interiors. And if our own solar system alone holds this many, then across the uncountable star systems of the galaxy, the number of such buried seas may be staggering, far outnumbering the rare, warm, sunlit worlds like Earth. This is the quiet revolution hidden inside the Europa story. For a long time, when we tallied the places in the universe where life might exist, we counted only the worlds that resemble our own, the planets sitting at just the right distance from their star to keep liquid water on a sunlit surface. We called that the habitable zone, a thin, warm ring around each star, and we treated it as the whole of the territory where life might gather. But the hidden oceans break that picture open. They tell us that liquid water, the one thing we thought required a careful place in the warm light, can exist far outside the habitable zone, in the deep cold, kept liquid not by a star but by gravity and time. The territory where life might exist is not a thin warm ring after all. It may be vast, extending out into the frozen dark, into every icy moon, with a tide to flex it and a rocky heart to warm its sea. We were counting only a fraction of the possible cradles. The real number may be immense. There is something in this that reaches beyond astronomy, something that touches the strange fact of being a small aware creature on one world among countless others. For most of human history, we believed we were the center of everything, that the heavens turned around us, that our world was the whole of what mattered. One by one, those certainties have softened. We learn the earth circles the sun, that the sun is one star among hundreds of billions, that our galaxy is one among uncounted others. And now we are learning that even liquid water, even the conditions for life, may not be rare and precious and ours alone, but scattered through the cold outer dark in sealed oceans we are only beginning to find. Each discovery makes us smaller and the universe larger and richer and stranger than we had dared to think. And now Europa adds its own quiet line to that long humbling. It tells us that even the warm, sunlit seas we thought were the special province of life may be the exception rather than the rule, that the more common cradle may be the dark, sealed ocean, far from any star, hidden inside a frozen moon. The center of the story keeps moving away from us, and each time it moves, the cosmos opens a little wider, and yet there is no real loss in that smallness. There is a kind of companionship in it. To learn that the ingredients of life may be turning quietly in the dark beneath the ice of a distant moon is to feel a little less alone in the cosmos, not more. And let us be honest too about how much remains unknown, because the honesty is part of the beauty. We have not found life on Europa. we may never find it. It is entirely possible that the ocean down there, for all its water and warmth and carbon, is sterile, a vast dark sea where the chemistry of life never quite took hold, where the ingredients gathered, but the spark never came. That outcome would be its own kind of profound discovery, because it would tell us that having the right ingredients is not enough, that life requires something rarer than we hoped, that our own existence is more improbable than we knew. Either answer changes how we understand ourselves. If Europa's ocean holds life, then life is common, the universe is fertile, and we are one note in an enormous chorus. If it holds only water and silence, then life is precious beyond measure, and the green film on our one warm world is rarer and more fragile than we ever dared to believe. There is no answer to this question that does not enlarge us. The mystery is generous that way. It gives meaning whichever way it falls. What we know for certain is only this. There is an ocean, it is warm, it carries carbon, and we are going to look. That is already enough to change the shape of the night sky, to make a small bright point of light beside Jupiter into one of the most interesting places we know. The next time you happen to see Jupiter in the evening, a steady bright star that does not twinkle, you might remember that just beside it, far too small to see, turns a frozen moon with a hidden sea inside it, larger than all of Earth's oceans together, dark and patient and possibly, just possibly, alive. The knowledge does not require you to do anything. It only asks you to hold the wonder of it for a moment, the way you might hold a smooth stone, before you set it gently down. Let your mind go down there now, one last time, into that sea no eye has ever seen. Above you, 10 to 15 miles of solid ice, a frozen sky shutting out the stars. No sunrise will ever reach this place. No light has ever touched these waters. There is only the slow churn of a black ocean, the faint warmth seeping up from the rocky floor below, the gentle, ceaseless flexing of the whole moon as Jupiter pulls it close and lets it go, and pulls it close again. Carbon moves through that water. Energy moves through it. The same simple ingredients that, on one warm planet long ago, somehow gathered themselves into the first living things. Whether they have done so here, beneath the ice of Europa, we do not yet know. The door is still sealed. The water still keeps most of its secrets. But a spacecraft is falling toward it through the dark, and somewhere around the year 2030 it will arrive to listen more closely than we ever have. The question is open. The descent has only begun. And here, as the night settles around you, is perhaps the quietest thought of all. You carry your own dark oceans within you. Even now, as you lie still and let your breathing slow, vast unseen processes are turning in the depths beneath your awareness. Your heart keeps its rhythm without being asked. Your blood moves through hidden channels. Beneath the surface of your waking mind, in the dark where you cannot watch, the slow chemistry of rest is doing its patient work, repairing, sorting, quietly keeping you alive while you drift. You are, in your own small way, an ocean world too, most of yourself hidden beneath the surface, the deepest processes carrying on without a witness, in the dark, while you sleep. There is one more thing to carry into the quiet, and it is perhaps the gentlest thought of all. Everything we have followed tonight unfolded slowly. The ocean took billions of years to gather and warm beneath its ice. The carbon took an unknown age to rise through the broken crust to the surface. The light took the better part of an hour to cross from the moon to our telescope. The spacecraft will take more than 5 years to arrive. Nothing about this story is hurried. It is all patience, all slow turning, all the long, deep time in which real things actually happen. And there is a kind of permission in that, a quiet invitation to let your own night be slow as well. You do not have to resolve anything tonight. You do not have to arrive anywhere. The universe itself works at the pace of ages, content to let an ocean turn unseen for eons before anyone arrives to wonder at it. You can let your thoughts settle at that same unhurried pace. Let them drift and slow and sink, the way carbon drifts up through dark water, the way a spacecraft falls without sound through the long reaches between the planets. Feel how small the rush of the day becomes against a backdrop like this. The worries that pressed on you this evening, the things undone, the words unsaid, set them for a moment beside a moon that has held its secret sea in darkness since before there were eyes anywhere to see it. They do not vanish, but they soften, they take their proper size. There is a whole hidden ocean out there, turning patiently in the cold, asking nothing, waiting without anxiety for the slow arrival of our curiosity. And there is a whole hidden depth in you as well, working quietly beneath your awareness, asking nothing, ready to carry you through the night, whether you watch over it or not. You can trust it, the way the ocean trusts the dark. You can let go. So, as you let go tonight, let the image of Europa go with you. A small, bright moon turning slowly around a giant planet, far out in the cold. Beneath its ice, a sea larger than all of ours, dark and silent and warm, holding within it the simple ingredients from which, on one world at least, life once arose. No sun reaches that water, no eye has ever seen it, and still it turns, patient and unhurried, keeping its quiet possibility through the long dark, the way the depths within you keep their quiet work through the long night. There is no need to resolve the mystery tonight. There is no need to know the ending. There is only the slow turning of a hidden ocean far away, and the slow turning of your own breath here in the dark, and the gentle knowledge that the universe is stranger and fuller and less lonely than we ever supposed. Carry it softly with you as the room goes quiet. A frozen moon, far out in the cold beside a giant planet. Beneath its ice, a dark sea twice the size of all our oceans, warmed from within, holding carbon, turning slowly in a night that has never known a dawn. We caught a whisper of it in reflected light. We are sending a machine to listen more closely, and the answer, whatever it is, will arrive in its own slow time, long after this night has passed. You do not need to wait up for it. You only need to let the image settle over you like a blanket, the dark water turning far away, patient and unhurried and utterly at peace in its own deep silence. Rest now. Let the dark ocean turn far away in the cold, patient and unhurried, and drift gently down into your own.